Hello everyone, I welcome you all. Now I am going to explain heat transfer through lagged pipe operators in our heat transfer laboratory. The main aim of this experiment is to find out the rate of heat transfer of same pipe having different cross sections and find out the critical thickness of insulation. So for that one, come to the description of the operators. The operators having the four zones. First one is the bare zone, zone 1, zone 2, zone 3. All zones are provided to the same pipe is provided having a length of 450 mm and each zone is divided into equally divided into 110 mm and thermocouples. 7 thermocouples are provided to find out the temperatures of surface temperature, inside and outside temperatures of the different zones. Here T1 indicates the bare zone temperature and T2 indicates the inside temperature of the zone 1 and T5 indicates the outside temperature of the zone 1. Come to the T3, this one is the T3 thermocouple. So T3 indicates the inside temperature of zone 2 and T6 indicates the outside temperature of zone 2 and T4 indicates the inside temperature of zone 3 and T7 indicates the outside temperature of zone 3 and T8 indicates the atmospheric temperatures. Come to the panel setup. This is the overall panel setup of this experiment. In this one is the console. So this is the main of the panel. The energy is distributed throughout the panel through this switch, and this one is the heater switch, and this one is the thermostat to control the power input to the equipment, and this one is the temperature indicator and channel selector. By using these two to know the temperature values at various positions, and this one is the power indicator to know the how much amount of power is given to the equipment. Let us go for the experimental procedure. Here I am giving the power supply to the equipment. Switch on the mains here. Console on and heater on. By using the thermostat, adjust the power input given to the bare zone. Fix the some amount of the power here and observe the readings here T1, T2, T3, T4 like that. Observe the temperature values at various positions of the bare zone. Observe here the temperature is varying with time. That means the equipment is in unsteady station. So please wait some time to reach the steady state condition. After reaching the steady state condition, tabulate the values here and go for the experimental calculations. These are the values recorded during the time of the experimentation. Initially, we given the power input, 80 watts of power input is given to the system, and the values are varied like this. Observe the last two readings here. The variation is very low compared to previous 10 minutes and after the 10 minutes, and we considered that these are the steady state values. Here I am rewriting the steady state values here. Totally 4 zones are there: bare zone, zone 1, zone 2, zone 3, and these are the temperature readings of the bare zone. These are the temperature readings of the zone 1, temperature readings of the zone 2, and temperature readings of the zone 3. And this is the thermal conductivity of whatever the material we used for the providing the insulation to the rod, and the material value of that thermal conductivity is K equal to 0.192 watt per meter degree centigrade. And these are the specifications for the experimental setup, and this is the experimental setup, and this is the rod, total rod, and this one is the insulation provided by varying the diameter, and this one is the bare zone, zone 1, zone 2, zone 3, and this one is the bare zone diameter, bare zone radius, and zone 1 radius, zone 2 radius, and zone 3 radius, and length of the each zone is 110 mm, and convert this into the meters, 0.11 meters. So let's calculate the rate of heat flow through the each zone. Consider the bare zone first of all. Observe here, there is no insulation provided to the bare zone. So, here directly heat is transferring from surface of the bare zone to the atmosphere. So, here the mode of heat transfer is convection. So, apply the Newton's law of cooling here, H A delta T. Consider the value of H. Here consider heat transfer coefficient H equal to 25, sorry, not a 25, 15 watt per meter square degree centigrade according to natural heat transfer coefficient experiment conducted in our heat transfer laboratory. So, same value is inputted here, and area equal to pi d L, and temperature difference is surface temperature minus ambient temperature. Calculate the Q rate of heat transfer through the bare zone, 15 into pi into diameter. Diameter is 0.038 into length of the zone 0.11 pi dl into temperature difference. Here the bare zone temperatures are there, 85 minus 29. Substitute these values here. Calculate by using the calculator. 11.03 watts rate of heat flow through the bare zone. So, same like that, calculate the rate of heat flow through zone 1. Q equal to, consider here we provided the insulation. So, heat transfer through the insulation. So, this mode of heat transfer, here the mode of heat transfer is conduction. Apply the here the mode of heat transfer is the conduction. Apply the cylindrical coordinates to this one. 2 pi k L into temperature difference Ti minus T naught, that means Ti minus T naught by ln of R2 by R1. This one is the formula of cylindrical coordinates. This formula is derived from cylindrical coordinates. So, substitute the whatever the values are there. 2 pi 0.192 is the thermal conductivity, L 0.11 is the length of the zone. Temperatures, these are the zone 1 temperature readings, and 139.1 minus 70.1 divided by ln of R2 by R1. This one is the R1 by R. Substitute the R1 by R here. 0.0325 divided by 0.019. Calculate this value by using the calculator. 16.57 watts is the rate of heat flow through zone 1. Calculate the rate of heat flow Q through the zone 2. Again same formula I am substituting here. 2 pi k L into temperature difference. Temperature difference is inside temperature minus outside temperature of the zone divided by ln of outside radius by inside radius of the zone. That equal to, substitute 2 pi k value 0.192 and length of the zone is 0.11 into inside temperature and outside temperature of the zone. These are the inside temperature and outside temperature of the zone 2. 142 minus 70.1 divided by ln of inside radius and outside radius of the zone. So inside radius is 0.019 meters, outside radius of the zone is 0.0375 meters. Calculate this value. (14.02 watts). Again calculate the rate of heat transfer through zone 3. Same formula I am applying here. So directly I am substituting the values here. 2 pi k is value is 0.192. Length of this zone is the same, 0.11. Inside temperature and outside temperature of the zone. These are the inside temperature and outside temperature of the zone values. 135.2 minus 54.3 divided by ln of inside radius and outside radius of the zone. This is the inside radius of the zone and this one is the outside radius of the zone. Divided by 0.019 and calculate this value. (13.32 watts). These are the rate of heat flow values through zone 1, zone 2, zone 3 and bare zone. Let us plot the graph and calculate the critical radius of insulation. After calculating the rate of heat flow values through the each zone, here I plotted the graph between the radius of the pipe and the rate of heat flow of each zone. Here I considered radius as along the x-axis with a scale of 1 cm equal to 5 mm and rate of heat flow is considered along the y-axis with a scale of 1 cm is equal to the 2 watts, and I plotted the graph like this. Here the maximum heat flow occurs at a radius of 32.5 mm. So we concluded that the critical radius is 32.5 mm and convert this into meters. 0.0325 meters is the critical radius for the lagged pipe.